The gravity is 1/8 millionth that of Earth. So that means if you get a quick run, hop, and jump, you too can play Superman or girl, because you go at escape velocity. Problem is getting back to your spacecraft on Bennu. Oh well. But if this thing hit Earth, and it might, or come very close, in the late 22nd century, the millions of pieces of that pile are going to rain havoc on our planet. You don't want to have that happen. Look what happened to the dinosaurs. That was only one hit that we know of, 66 million years ago. And it wiped out about 80% of life on Earth. Now this is more fragmentary, but it would cause incredible havoc anyway on Earth. Okay, give you an idea. How many people go to MetLife Stadium? Okay, a couple of people. Okay, you know how big this thing is. Look at what's behind it. That's Bennu for scale. You do not want to see this in East Rutherford, trust me. Okay, so why study it? Well, even though it's out there and it can sort of get close to Earth, but there is a law of physics. It's called the Yarkovsky effect. It is actually spinning on like a top on its axis like planets and other asteroids, but it's going backward. And because the radiation of the sun comes up to it, heats it up, it creates drift. That drift changes its orbit, which means that sometimes it will pass very close to Earth, and it's getting closer. Okay. Late in the 22nd century, this is shamelessly taken from a movie poster called Armageddon, I think it was. And New York City is about to go the way of the dodo and the dinosaur if we're not careful here. Did not happen in the movie. Spoiler alert. But there are 8 opportunities between these years, between 2169 and 2199, that it could crash into Earth. And the more time we have to prepare for that, the better our chances of survival, and maybe the entire planet as well. Okay. They can't just blow the darn thing up. Radar shows it's a rubble pile. Gravity holding it just barely together. To blow it up makes thousands of meteorites, everything from something the size of my fist or smaller, all the way up to the size of this building, perhaps, and even larger. And there's no easy way to stop them all. The Enterprise and her sisters are not going to come out of nowhere and use their phasers to destroy them, because it would just make them smaller particles. Nobody notices that when you watch any of the Treks. They fire phasers, and the thing blows up. They don't show you where the pieces go. They're all over the place. You know, you need a disintegrator, and we don't have that. Real science fiction. So we got to plan this out, and at least we have some time. Okay, because if left to itself, it would devastate the planet from impacts around the world, damaging the ozone layer, which we need to protect us from the energy of the sun, and severely cooling the Earth for years. Okay, now we had past missions to asteroids. Near Shoemaker, near Earth asteroid reconnaissance is what this name means. This gentleman's name, Gene Shoemaker, was a pioneer in a relatively new science, the study of astrogeology, the study of the Earth relative to other worlds, and it also extended to looking at the asteroids. This object came very close to 433 Eros, which is another potential problem, but that's like about 26 million years into the future. We're more worried about stuff that's happening, or more or less about 2 or 3 generations from now. Maybe. Okay. Dawn went to 2 spacecraft went to 2 objects. Dawn was at 4 Vesta, which is actually one of my favorite asteroids. It's easy to see. If you're in a really dark sky area, you can see it naked eye at the proper time of the year. And then 1 Ceres. Ceres was the first asteroid discovered, so therefore it gets 1 Ceres. This is the 4th object. And these are both spacecraft photographs from the Dawn spacecraft. Okay, so it's time for a sample return. See, the problem with this is that unless we have seen it fall to Earth, and we're able to, by photographing the path of it in the Earth's atmosphere relative to the sun and relative to Earth and such, we can usually find out where a meteorite came from. Meteorites, for those that don't know, are rocks and metal that come from space, usually leftovers from the creation of the solar system. I have samples of them up here. You can come up and take a good close look. But in this case, we did a very close look. It was time for a sample return. And basically, the probe would study that, the original name for RQ-36, I apologize, I got to update that slide, would be there, was there for over 500 days, mapping the entire surface and taking samples with a robotic arm. So there's a sample return capsule and a sampler which came down, and there's a movie of it as it comes and approaches, goes in and comes out, and we'll talk about that a little bit later. That almost didn't happen. Okay, so the mission objectives. Return analysis a minimum roughly 2.5 ounces, 60-gram sample of the pristine carbonaceous carbon-containing asteroid regolith. A regolith is a crushed rock. It's not soil per se. Soil here on Earth and any other planet maybe that has it is about half rock and half organic material. In this case, it's a different type of organic material. It's not created by life, at least as far as we know. But in this case, it's to study the nature, the history, and the distribution of its minerals and organic material, if any. Map the global properties, the chemistry, and mineralogy, the study of rocks, of a primitive carbonaceous asteroid to characterize its geologic and dynamic history and provide context for the returned samples. Let's translate that. It's a grab sample. It brings it to Earth. It comes into our laboratories, and then it's studied there. A spacecraft is good, but it ain't that good. Not good enough to be able to start differentiating different chemicals. Is the organic material we see here from here by accident, or was it created out there and has come from out there, for example? And how did it change, the dynamic history, as they call it? There are other asteroids, you've seen the pictures now of Vesta and of one Ceres. If it craters, it'll change the chemistry. It might even add the impactor chemistry to whatever object we're looking at. So we wanted to find out everything we could, at least if we had the sample, we could get a lot of information just from that. Okay. Also measuring that wonderful effect, the Yarkovsky effect, a thermal force in the object on a potentially hazardous asteroid, and this is hazardous, and note the properties that contribute to the effect and the properties of a primitive carbonaceous asteroid to compare it with direct observations with telescopes on the rest of the population. Another English translation. We want to go out there, find out as much as we can about the object, its composition. We want to find out what it could do if it did get very close to Earth or hit the Earth. Okay, this is an overall view of the spacecraft. We have other photographs later. The basic idea is that the collection system is up here. It has solar arrays to power it from the sun. We're going to go into the different instruments here rather quickly. And it even has thrusters and a star tracker so it can see where it is and then correct its path. Okay, and it'll take more than just pretty pictures. For example, at the top, SAMCAM, images the sample site, hence SAM. The documents the sample acquisition as it's going in. We want to see what happened. There's a lot you can learn from just digging into something and watching how the soil moves around. And images TAGSAM to evaluate if the TAGSAM had actually got a sample. NavCam gives you navigation and filter, photometry, photographing different colors of light so we can compare it to known materials here on Earth. Polycam is a long-distance camera from over about a 500,000 kilometer range. It does optical navigation. That way we know where we are as we're moving along. OLA over here provides ranging data up to 7 kilometers. It allows us to be able to see the asteroid and image it so that we can get an idea of where we want to land. Sorry. No cheating. Okay. The thing that I like myself up here is OSIRIS. This maps the reflectance, albedo, its reflectivity, and light properties from 0.4 to 4.3 microns. In other words, it looks at it from the deep violet all the way into far into the infrared. And again, you can tell minerals even indirectly that way. OTIS measures the thermal flux, how much energy goes in, how much energy comes out, what's it's absorbed, and what materials maybe are doing that absorption. The radio science is cool because as it's in orbit, we track it as it moves around the object like this. It reveals mass, gravity field, internal structure, and surface acceleration distribution. In other words, how fast would you come if you came too close to it, and how fast would it pull you in? And how do you compensate for it? Rexis measures elemental abundances of the asteroid's surface. This is what I was really more interested in. What's it made of? That would tell us roughly where it came from. So tag SAM bringing Bennu safely to Earth. Yes, I know. In 150, 200 years, it'll come to us. We can't get a big catcher's mitt, folks. And we don't want that. We don't want it to come in uncontrolled. Maybe even we may have to push it out of the way. So tag SAM would bring some of the materials safely to Earth. Now, this is in the laboratory up here. And basically it has, I think the next slide shows it. It shows carefully pressurized nitrogen as it touches down for a few seconds and blows material into holding containers, and this is an experimental attempt with it, and it worked very nicely, at least in the lab. And this is how it works. There's a mylar flap that, as the gas from the nitrogen container lifts up, pushes the regolith to flow into the compartment down here, goes up and in. The pressure of the gas regolith causes the flap to open up. And the gas, as it closes, when it moves away, it escapes through a mesh which keeps the sample in place. And the gas flow agitates RQ-36's, I gotta change that, surface. It flows in, and this is how you get a sample back. To make this project a success, quote unquote, we had to get 60 grams, roughly about 2¼ ounces of material. And we'll get back to that in a little bit. Okay, and they tested it on Earth, and as you can see in this picture, see this guy's playing tag SAM over here, and he's looking down at the collector of it, and looked pretty darn well to me over here. Okay, and then return to sender. The heat shield, just translating this quick, the heat shields here, the whole thing, the structure, could withstand almost 5,000 degrees temperature as it comes back into the Earth's atmosphere to slow down. The canister with the sample head was embedded in here. Capture mechanism, basically, as it goes in, it locks it down so it's not going to bounce around in there. The avionics that control its path when it goes into the Earth's atmosphere, and the latches that seal it up completely. Okay, and the whole sample is done in a 5-second touch and go maneuver. Just basically came down, touched down, and this is actually a spring, not an arm. And after a few seconds, about 5 seconds or more, rebounded from the surface using that spring stored energy, and it's able to approach the surface within certain constraints of speed, and it could then fire thrusters to get away from Bennu. It's a good thing it could, because I'm going to be talking about that too. That almost was a disaster. Okay, so this is just an overview of the mission timeline. You know, this is not like the old science fiction movies where they have astronauts training to go someplace, and they climb into the rocket, they jump in, they strap in, and go. This is all inside maybe 20 minutes in the first part of the movie. Good luck. It don't work that way. We don't have something on the pad to go up in. In this case, you had to go through committees. Back in 2011, they decided they were going to do this. They went through review designs, critical, etc. Launch in September 2016. It would take till 2018 to get there, and then departure in 2021. And then get home, and it is back, and we'll talk about how that came later. And then the end of mission technically is in September 2025. The reality is that the analysis of the rocks and specimens some of it's going to be held for future generations, just like we did with Apollo. Out of 840 pounds of lunar materials, not quite 30% has already been analyzed. And this is to allow for the fact over the years that the technology we have now is far superior to what we had back in 1970-71. So we look a little bit further, and sure enough, we'll have better tech, hopefully. Okay, the mission was half over, but they already started talking about this just recently. A proposed OSIRIS-REx 2 sent a sampling mission to the moons Phobos and Deimos of Mars. They believe that at least one, maybe both, are actually samples that were blasted off from the surface of the red planet and what fell into orbit around Mars. And it would be kind of cool getting samples there instead of having to go through the problems and worry about entering into the Martian atmosphere, landing safely, going out collecting your samples, and then getting back to a rocket and blasting off. Here you just go quietly to one or both objects and then hit thrusters and come back to Earth. Total mission time maybe about 5 years. Not bad. Okay, meanwhile, at another asteroid Ryugu, this had a vehicle, there we go, which was ready to explore, Hayabusa, It's from the Japanese Space Agency. And this is just an overview of their work, solar panels again, and a sampler horn as it was referred to. Again, using pressurized gases to be able to get some samples in. There have, for close approach, near-infrared spectrometer to analyze what it was touching. Laser radar to allow it to know that it's coming in close and to hit the jets to slow down just enough so the vehicle will not crash and then be able to lift off again. And just another view of it. There was a lander that was attached to it. I haven't heard that much about it, but I believe it was successful. The rovers did not deploy, unfortunately. Shame that. It would have been kind of cool getting a mouse's view crawling across to the surface of Ryugu. Okay. And oh yeah, one thing I like about this too. It has ion drive. Yeah. What you see in Star Trek. Scotty's saying, it must be ion power. That's the only thing that could do this. You know, it's actually quite weak. However, you can fire it for a very long time, and that allows you to build up speed or to lose speed as you're approaching a target. Scotty had half the equation, not the full thing. Okay, so sampling an ancient rock, multiple photographs. Here's the collector coming down, and right after touchdown, they'd also use nitrogen gas to take a sample of the surface of the asteroid. And Hayabusa 2 returned samples to Earth on December 5th of 2020. It's a nice overview. The vehicle itself just returned the samples. The vehicle here, I believe it continued on. I'm not sure if it was retargeted. You can't collect more samples, but you can go to another asteroid, so you get more bang for the buck for the money invested. To tread the soil of the asteroids. And this is the sample that came out. This is a good scale over here. These are tiny little pieces about that big. I'd kill to have one of these things in my collection of meteorites. And I may have that. Like I said, these carbonaceous guys over here may have come from there. And we'll talk about that too a little bit. Okay. Well, the main spacecraft was sent to another target. There we go. And, okay. This is it. See, there's no name with it, so I go by names, I don't go by numbers, unfortunately. This is asteroid 1998, the discovery year, KY number 26 in that particular month. About 100 feet in diameter, a little bigger than this building total. These are images from the Subaru 8-meter telescope. 8-meter mirror. Wouldn't even fit inside this room if you could hollow it out a bit. In 2020, when it was about 250,000 miles from Earth. That's the best guess. Stay tuned. Okay, size comparison. Okay, there's Ryugu over on the left, and on the right is Bennu, our target here. Okay, Bennu boulders are big. When you look at them in the pictures, but when you have radar so you can give a scale, that's 20 meters. Look how big this thing is. It's about 60 meters, 60 meters across. Over here, 8 meters. So you're talking almost 20 meters across. A meter, by the way, for those who aren't familiar, is about 3.3 feet. So it's about a yard. Close enough. So there are large chunks all over the place here. And it isn't friendly. Look at this. This spacecraft went through the trouble of going through the Earth's atmosphere, building up speed to go out to this object. Took it a couple years to build up enough speed to get out there, fall into orbit, and what happens? The asteroid throws rocks at it. We think that there was water actually underneath here, and it just so happens that every so often it gets a little too warm, and the water flashes to vapor and pushed all the rocks out there. And the navigation people are having heart attacks saying, oh great, we go all this distance and the last picture is this rock coming right at you. Well, it didn't happen.
Is this an actual photo?
This is an honest to God photo. Yeah, but luckily after, maybe it saw the spacecraft and said, okay, stay back. And that was it. I don't know. Go up. We got to ask the asteroid. Anyway, yeah. So it's stay back. Who knows? Okay. But so it turns out what happens is that sunlight can actually break up rock up there. It's so fragile. A little bit of water, and there is some water in those rocks, will actually vaporize at the right point. Just happened to be we got there at the wrong time. Or maybe the right time, because none of the rocks hit the spacecraft. There you go. So Bennu's rocks are similar to CM2 carbonaceous chondrite meteorites, which contain water and are very fragile. You could take a sample of this, and it would break my heart seeing somebody do it. Take a sample of one particular meteorite that fell in Murchison, Australia. in I think it was about 1969. And it's big and it's nice, it's beautiful. It smelled horrible because there was so much organic material in it. And one kid picked it up. The story goes, he played Superman. He says, watch this, and he actually crushed it in his hand because it's that fragile. We got very lucky. 220 pounds of what was probably a ton of rock made it through the Earth's atmosphere that day. Now, I do not have a sample of the particular meteorite I mentioned here, Murchison, but you can look it up. And I do have one that in February of that year did fall to Earth. Got it right here. It's called Allende. It was fell in Pueblito de Allende, Mexico, and it shows a lot of the evidence that we've seen on some of the samples that were returned from Bennu. Aguas Zarcas fell in 2019 in Costa Rica, and you will see it's very, very dark, just like these materials are too. So I brought these here because most people probably, unless you deliberately go to a big museum like the Museum of Natural History in New York or the Smithsonian, or maybe in the Boston Museum of Science, it's unlikely you're going to see them in a rock collection somewhere. So I brought a few pieces in here. But Murchison is the best analog we have to it. Not only does it have water, and if you took a sample of it, I hate anybody that does this because I've seen it done once and it's awful, because you put it in a test tube and you heat it up, and the water that comes off from it that collects at the top of the cool part of the test tube is water, not of this Earth. Very different, a slightly different type of hydrogen that's combined with it. Standard H2O we can drink. Heavy water like they use in nuclear reactors, that's poisonous because our bodies cannot absorb that hydrogen. Here is where you're seeing a lot of that heavy water. It's very strange. But weathering the rock, you can see where there are cracks and fractures all over the place. There's one that's going to pop right out right there. And you can see how big they are too. So this is really an amazing thing, and it fractures it over time. That's how it was able to throw rocks at us, basically. We just got there at the right time, or wrong time. And here was a surprise. One of my favorite asteroids is a rather bright one called 4 Vesta. It's the 4th one discovered. I think it was in 1806, if I remember correctly. The optical visible camera had determined that these boulders here, these are meters across, okay, a couple yards each, probably were swept up from a vestoid asteroid, in other words, a chip-off Vesta, and there's reason to figure that out. This is a 2-for-1 discovery. So we go to one asteroid. It's a shame they didn't have another collector. It'd be cool to get a sample of this material so we don't have to go all the way out to Vesta, at least not immediately. Hell, I want to go out there anyway. It would be fantastic work. So we made discoveries even before it even left the asteroid. But now we got to decide, where are we going to touch down? Since Bennu takes its namesake from an Egyptian deity, and it's a bird, they decided, where we should go. Should we go by nightingale, sandpiper, osprey, or kingfisher? Now, to be honest about this, I like sandpiper because it's all full of sand and fine grained material. What they did choose, though, was nightingale, which is fine. Come on. There we go. So here's how they were sampling in here. The entire movie shows it. This is the moment of contact now. And it went in. The problem was we didn't realize at the time, it kept on going. And luckily, after 3 seconds or so, the thrusters fired and pulled that collector out of the regolith, out of the rocky soil. And after the point of contact, this is what it had left it. So it went in, pulled out a sample. To make this mission a success, quote unquote, they had to get 60 grams, about 2¼ ounces of material to return home. Okay, TAG-SAM did its job. It went in there and it grabbed the sample and it got too full. There was a mylar flap that should have closed. You can just about see it over here. And they said, it's too full. It's leaking. It's dropping everything left and right. So, quick, pack it up. And that's exactly what they did. They put it into the sample return capsule here, loaded, and then closed her up and sealed it. Then the return was back in September of 24th of 2023. Came in hot and heavy. and landed, thanks to Lockheed Martin and other people, in the Utah desert. And there it was. I mean, this is incredible. And one of the parachutes actually did not completely deploy, but it still landed perfect. Look at that. I mean, I've seen much worse. They had recovery capsules that the parachute didn't deploy, and it just crashed in. And they were able to get data from it, but they lost a lot too, so it happens. This one worked. Yeah.
Is it black like that from the re-entry?
Very good. That's exactly right. That's right. It's black because it's charred. When it came in, they figure it hit at the most intense entry was about 5,000 degrees. Yeah. Even tungsten has the highest melting point. It would have softened and started to melt. It would have vaporized. It was a little bit hotter, about 6,200 degrees Fahrenheit. But here it is, waiting for somebody to pick it up. And there's recovery. And I am happy to say that it wasn't just a bunch of guys going out into the desert. It was men and women that went out there, and they were trusted with probably the most important part of the entire mission, making sure this got into the helicopter to bring it to an airplane, to a jet, to bring it to NASA so it could be properly processed, and it's still being processed right now. But I think it's terrific. It's about time. This isn't a boys' club anymore. Humanity has to do it together. Okay, finally, in the lab, we are there. And there it is, opened up in a very special clean room environment. Before they opened up the capsule, they were examining the outside. They cleaned it up. And here they are just starting to open up. They got the lid off in this case. And everyone else is out here. And of course, anyone who's ever saw science fiction, when they open up the capsule, suddenly things happen, tentacles come out. Then let's tell you where they got tentacles from. You know, or infectious diseases that wipe out the universe or some nonsense. It don't work that way, folks. And then NASA, using the best knowledge we have about current creatures down here on Earth and microbacteria and viruses, we can clean them up. The Andromeda Strain is a wonderful movie. In fact, I think the book was better, but for once. But that's science fiction. This is reality. Okay. Archiving specimens, it was rather cool because I opened it up, and some of them almost escaped as well. There it is. Some of the material. But that's not the sampler. This is the excess that was starting to leak out when it filled it up too much. Here, see some of the excess. There it is. It's a good close-up. Some of the material still hanging in there, and I'm looking at this, and I'm saying, I want that piece. I want that piece. I definitely got to have this piece. But, you know, then I'll listen to amateur collectors. Okay. But it didn't want to open up to show the good stuff, the main sample. Now, you would think that, okay, they just get a bigger tool, and there's the bigger tool. Well, that tool had to be made custom made. They didn't have one to open it up like this. So the steel had to come from a particular type of alloy whose properties were well known, chemical, physical, metallurgical. They had to make it match what the spacecraft itself was. And that took about another 2 weeks. And talk about impatience. Everybody's saying, give me a can opener. But in this case, they made it work, and they got it in there, and sure enough, they opened it. This is what they got. There's pay dirt. Literally, pay dirt. And it's 240 grams of material. It was supposed to only get 60. So it not only did its job, it did its job exceptionally well.
So it's soil. It's fine soil.
Well, it's soil and rock. And actually, it's not really soil. Again, it's called regolith. It's rocky material. There's almost no organics from growing plants, and they die and form the soil. But it is mostly a rocky material, and it has chemicals in it. Whether or not they were alive is another matter. That's what's being studied right now. But I look at this, and again, I say, I want that piece, I want that piece. I got to have that one. And there is actually 1 or 2 white fragments in there, too, which may have come from Vesta, and again, it's one of my favorite objects to view. And selected views, it gives you a good sample, just how big they are. There even seems to be here, that surprised me, water-bearing clay materials. Clays are a strange chemical composition. We have them on Earth. They're all over the place. Sometimes they're formed from life, sometimes they're not. There are other things here. There are sulfide mineral planes right through here and up through here. Okay, iron oxide, which actually they expected to see something of that because iron is rather common in the solar system. And then there are plaques. If you look carefully, you're seeing layering. I wonder how that happened. Okay, final samples underneath the main deck. They found more material. Like I said, 240 grams returned. And we only had to get 60 to make it successful. And this is great. Well, where can you all go right now to see samples, or at least a sample, that OSIRIS-REx returned? And that's easy. There's a sample in the Smithsonian down in Washington, D.C. Specimen number 860027, 5/1000th of an ounce, is sealed in dry nitrogen in a container made of copper with a quartz window. Now, you'd probably be saying to yourself, okay, Al, why didn't they use aluminum, or why didn't they use stainless steel? You know, if they're worried about corrosion or something or affecting it. Well, that's the reason. We're worried about materials that chemically can vary. So it was made out of copper for the main holder here for a big reason. Copper cosmically is extremely rare. Oh yeah, there's a mountain that's, I believe it's in Colorado, which used to be a mountain. Now it's a big valley because we've taken all the copper out of it, and there's still about 150, 200 years worth of copper waiting to be mined from it. So on Earth, yeah, you got a couple big pieces of it, but in space, there is only one meteorite that has been found on Earth. Fell, I think, around 1949. Fell out in the Arizona, I believe, desert. And unlike most meteorites, when you find them, they're freshly fallen, you pick them up, most people say, oh, it's hot, it's cold, unbelievably cold. It even gets frost on it sometimes. That particular copper meteorite was hot. Makes sense. High conductor. So we know the composition of that holder, the copper in it, the alloy, the different impurities, all the stuff is documented. Quartz is chemically pure silicon dioxide, like sand. But this material is chemically pure, so we know its composition. And we know the composition of the nitrogen. There are different isotopes, so they separate it for just one type. So when they finally take this out off the display room, where you can go and you can see it, and under it they have a nice magnifier so you can take a look at it. I haven't done it yet, I'd love to. They know that this is maybe contaminated from here and here and here, and they can subtract that from the analysis of the piece in the future, which is really cool. Okay. In Houston Space Center, just opened. This display of a sample of it is ready for the aspiring explorer to see and to dream. And samples right in here. This is it here. This is a stylized view of it coming up to the surface of Bennu. These are all real photographs. And then right here with a magnifier. And there's a closer look. That's another small piece. One small piece for a spacecraft, one giant leap for humanity, maybe. Okay. And a third sample I haven't heard yet, but it's supposed to be at Kennedy Space Flight Center soon. Very much like the Apollo moon rock, so about 70% of everything that was returned is going to be archived for future researchers and newer technology. Because the technology now, the mid-2020s, is being used on Apollo rocks, and we're finding even more information now that we never dreamed of with that. And that'll be another lecture sometime, so you got to come back, folks. Okay. Okay. And now where to next? Asteroid Apophis is going to make several close approaches to Earth in the 21st century. Some people are calculating right now it might hit the Earth in the mid to late 22nd century. So the renamed spacecraft, OSIRIS-APEX, Asteroid Apophis Explorer, will orbit the asteroid in 2029, exploring its composition, helping us in the future to safeguard our planet. Now the thing is, we can't take home a sample. Somebody should have put another sample return on it, but it's the way it is. Hopefully we'll get something out there, because again, that kind of a dangerous thing you don't want to let just float around, if you will. Okay, and how big is that asteroid? There it is. That's New York City skyline, and there it is, waiting, watching. You never know. Okay, and beyond pure science, there is a practical reason for diverting an asteroid. resources are waiting for us to, if you want to depollute the Earth, you want to take sample, get metals from somewhere else and other chemicals, the asteroids are out there, and if you won't let them crash into you, you might as well take them apart. You're doing it for duty and humanity. And here we have lots of materials. For example, you have hydrogen, carbon, nitrogen, oxygen for chemistry, volatiles and water, fueling the growth of humanity into future frontiers, building spacecraft in space instead of having to lift them up and put them together and then go off. You could build them right out there already, and maybe even put a service as space platforms like space stations. And there are platinum group metals, gold and silver, and platinum and iridium that are needful here. And we could find them. You need them in catalytic converters. Yeah, there's platinum and palladium in there too. I forgot palladium. LCDs operate off those materials. There are advanced materials that could be worked in chemistry and even cancer treatments. Imagine that. An asteroid that could menace life on Earth might give us the key, just might, to be able to cure a death sentence of cancer. Now that's a gift of the stars if I ever heard of one.
Is that just speculation?
That's hard fact. That is hard fact. We already know that there are certain platinum group metals that can at least arrest some cancers. Now we just have to figure out how to extend it. But it's going to, again, you know, platinum these days is more expensive than gold. Look at your catalytic converter. Somebody rips your catalytic converter out. What is it, $3 grand? What do you think? I collect them anyway. But here's the point, though. Whoop, sorry, got ahead. The point, though, is that the metals are out there. Cosmic on Earth, they're not exactly easy to find. They're actually cosmically rather common, and all you have to do is get out there, process them, and work with it. And you depollute the Earth. You don't have to go digging in mines and such. You don't have to worry about toxic materials, because if you have them, you don't send them to Earth to pollute the planet or something. You just fire, if necessary, fire it into the sun. I guarantee it will not come back. Okay, so you can do this. This is partly speculation, but it is also based on fact. So stay tuned. In closing, there it is. We rediscovered how much people love exploration. Or the way I look at it, put the rocket on the pad, guys, I'll take it up. And Alan Stern is a planetary astronomer extraordinaire. He has inspired many, many students and people. He's still doing it. And of course, Carl Sagan. And I have to thank my wife, Bonnie, for production work, a friend of mine at our other club, another club, Amateur Astronomers Incorporated, fellow observer and photographer. Michelle Toffel was an educator. She's retired. And lucky for her, she could do it inside 10 years. An inspiration, of course, NASA, Jet Propulsion Lab, the European Space Agency. We're not going up there alone. We could use help from other countries, and we are getting it. So a little bit of luck, instead of competing in wars down here and stomping on each other, and doing stuff that Og has been doing since 50,000 BC. We go up there, and the only competition there is to get there to say, I put my flag over here, and let's take this thing apart. Let's build space stations. Let's build more vehicles for exploration. Let's learn how to cure disease, how to feed the hungry on Earth, set up colonies on Mars, in the moon, and in general, make Star Trek look like speculative fiction when the reality is even better. And I thank you very much for your attention. Good evening. Okay, now, as I mentioned before, I have specimens up here that after we're done here, because I'm going to take questions in a minute. Come on. Okay, so you'll be able to get up here and get up close and personal with 2 meteorite specimens that are very similar apparently to Bennu, and then the 3 set over here, which basically talks about the 3 basic types of meteorites that you would find, maybe not in your backyard unless you live in Arizona, because then you have meteor crater in your backyard and the thing lands. Got stuff everywhere. By the way, you can't collect around the crater. Sorry. But of course, if you go on property adjacent to it, and the owner of the land says you can go and collect, and you find something, it's yours. But that's another story. Okay, so you'll be able to get up. So if anybody have any questions, I could try. Go.
So
to answer.
At the beginning of this slide, this presentation mentioned the defense aspect, and the aspect of getting a sample of the asteroid to see what it's made of,
Mhm.
etc. I totally understand mining asteroids. That's obviously way better than mining on Earth.
Mhm.
And the asteroids are endless. So, if we can figure out how to do that, that's awesome.
Mhm.
But what does getting a sample of an asteroid, how can that practically provide answers on how to defend from that asteroid to hit
Okay.
us? I mean, it's metal and rock. We know
Okay.
that. It's going to be metal and rock when it comes to hit us.
Mhm.
What
But
does it change that we
well,
do this?
if you saw the other slides that came after that particular, I know the one you're talking about. The idea of the asteroid either being a solid object. I really should have put other asteroid pictures in. That's my fault. This particular type is a rubble pile, which means that all these materials just came together, held very, very loosely by gravity, their mutual gravity. If we can get to them before they get to us, we can slowly but surely move them using solar sails, for example. Attach it to it, uses light pressure. The same thing that would doom the Earth from hitting it now can be used to control it, put it into orbit, say around the moon, which might be cool to watch from here on Earth, and then be able to take it apart if necessary, get the metals out of it, see the stock market go way up. Oh, the whole thing. That's pretty much how we would have to do it. If it's a solid object, and there are quite a few out there that are not rubble piles, and they do get close. 433 Eros, I didn't have a photograph to show here, though they are available on the web. That's almost completely solid, and that could hit the Earth, so that's going to be millions of years into the future. But imagine something we don't know right now, and we discover it, say, last night, and now we find that it maybe 100 or 200 years into the future, it is going to hit. Then we can go out there, we can change the orbit, and again, take it apart. Might be even easier because it's not rubble pile now, it's solid something, solid minerals and such. So that's basically the fast answer. There are many others too, but the best one is that we can do this, and actually we should if we want to maintain our ability to exist as a species. Because one bad asteroid on Earth will ruin your whole day. Trust me. Okay. Anyone else? All the way in the back, please. Hi.
How would we calculate that far in the future if an asteroid is going to hit Earth?
I'm sorry. Would you say that again?
How could we calculate that far into the future that's going to hit Earth? Like, over 200 years?
We know the mass of the planets and the sun. That has been determined many, many years ago. We can get an idea of flying a spacecraft around an object and see how its orbit changes. We put it into a particular orbit, and then if it starts to get a little elongate, we can trace back to where there may be some heavier minerals in it and affecting the satellite. So we can get an idea of the mass of the object, not the weight. Weight on Earth is relative. The mass of it. That'll tell us how dangerous it is, how we have to be able to use force to move it. Nuclear power. There are nuclear rocket engines on the drawing boards right now. In fact, two or three of them have actually been tested, and they work very nicely. So you attach one on this and change its orbit so it goes into a safe orbit around the Earth, and then you can go for it. But that's essentially the short thing. We watch it, we observe it. Put a spacecraft around, it's even better, because now you get a radio signal. And as it's moving, you can track it, even if it goes almost completely behind the sun. Get an idea of its orbit and see where it will end up in future years. And that's for all objects. Yeah.
So, if like in classic physics, a 3-body problem is considered impossible, how is like a potentially 50-body problem of all of space? We can track it accurately 200 years into the future.
Yes, you can. Our supercomputers, 3-body, there's always going to be a sense of error. But if you look at it just the sun, the Earth, and the object, that's 3-body again. Yeah, it may not be the most accurate, but as it gets a little bit closer in, as you observe more and more, you'll be able to add more data to it and then kind of tweak the numbers. If it's coming straight at us tonight, we're in a small amount of trouble. And something like that's when science fiction and fantasy all merge with the reality of, unfortunately, of nuclear weapons. But that's the only power we have to move it, and if we have enough time. That's why we observe it, because if the thing's coming at us and we can confirm it, then we know where it's going to be at a given time at a safe distance. Just push it. You don't have to blow the thing up. This is not trying to create a new Krypton or anything. All you have to do is heat up one side of it, and that energy will vaporize it like a rocket engine. It'll push it away. It doesn't take much, as long as it's far away. This isn't like, again, science fiction. The asteroid's right on top of us. It's about to hit, and suddenly they blow it up and it splits and goes away. Doesn't go away. The stuff is still there, but that's a good, very good question too, by the way.
Very good.
That's excellent. Anyone else? No?
I'm good. Thank you very much.
Okay.
Do you
Yeah.
remember the,
Yeah. I'm sorry.
do you remember the mission they just had about 2, maybe 3 years ago where